Welcome back. You might have seen these billboards which are digital, and you might have seen wherein like these billboards you can show different kinds of ads from different angles, especially during like a soccer match or a football match or cricket match. Have you ever wondered how these things are placed though they are moving in 3D and while players are moving around? At the heart of all these things are called transformations, and in today's episode, we will demystify transformations. So, the world is full of transformations. You transform in your mind, you transform things in math, and today we are going to see, in the context of computer vision and image processing, how you can transform one image to another to make it look seemingly like 3 dimension, though it is actually being transformed in 2 dimensions. So let's start simple and we will build up this concept as we go along. Let's say we have an image I1 and let's say we have the other image I2. In this particular case, they're both the same. So the transformation between them is identity, which means that they're the exact same thing. So what if I move my second image like this? In this particular case, I have dimmed out the image 1 and I've shown you that they have moved with respect to each other. I want you to pause the video for a second and think about what kind of a transformation this would be. If you have ever taken a math class, this should be fairly simple. If not, I just want you to intuitively understand what is actually happening here. So in mathematical terms, this is called a translation only movement. So we'll see how this is written in math. Let's take the 2 points which are corresponding in both the images. And if we represent the location of this point as this bold x, which is x and y, we want to come up with a function x2 in the second image, which will be a function f of the point location in the image 1, x1. Awesome. So what we want to do is we want to figure out what this function f is. For that, we will need to know how much this translation is, and I'm going to denote it as t1 going to 2, which is translation of the second image in the first image frame of reference. This is a simple vector addition. If you have ever worked with coordinate transformations, this is like basically moving the origin of that coordinate transformation. So x2 is simply the sum of x1 and t12. So if we want to like write this down in image processing, we write this with something called as projective geometry, or we call this homogeneous coordinate system, wherein we append a 1 to both x2 and x1 and put this transformation t into a matrix H, which will be a 3x3 matrix. And this is what it looks like. And H is again a real number 3x3 matrix, and it's a fairly simple matrix. It's going to be like this. So I want you to pause the video for a second and answer the question, how many free variables does this matrix H have? The answer is absolutely 2, and it's fairly simple. You can see that it's the t1 to x and t1 to y. So how many equations would you need to actually solve for this transformation t? The answer is again 2, because 2 equations will give you the solution to this matrix. How many point pairs would you need for this? The answer is 1. Single point pair will give you equation in x and equation in y, hence you can solve this directly. And it makes sense because simply given 2 points, you know the translation vector between them, and it's going to be the same throughout the entire image. And it doesn't really care about the location of the image as much. Okay, let's do a little more advanced, wherein we do a rotation with respect to the center of the image, and this is going to be out of the plane rotation, right? Or in other words, in mathematical terms, this is called yaw. Let's look at the same 2 points from before, and this is what the transformation looks like. I want you to pause this video for a second and think about, if I were to do this with coordinate frames, how would the transformation look like? The answer is fairly simple. You would take the axis on the second one and basically project it down using your standard trigonometric equations, and it's going to look something like this. And if we write this out as a matrix form, it's going to end up looking like this. And I wanted to pause the video for a second and think about what the H would look like. Again, as you would think, H is fairly simple. You have the cos of theta, sine of theta, minus sine of theta, cos of theta, 0, 0, 0, 0, 1. And here theta is the angle in the anti-clockwise direction with respect to the horizontal x-axis. So we have a single variable here, which is theta, as you see. So we need a single equation, and we need the minimum number of point pairs, which is 1. Awesome. Let's add both the things we talked about together. This is also called as the Euclidean transformation, or SE2. It's special Euclidean of order 2 because we are doing the transformations in 2 dimensions. So we do rotation first, and then we do translation next. So I wanted to pause the video for a second and ask the question, how can you put the rotation and translation together? The answer is actually fairly simple. H is going to be denoted by the multiplication of the rotation one we saw before and the translation one we saw before. So the question is, in this transformation, if you take the image 1 and image 2, what doesn't change under this transformation? Or in other words, what is invariant? The answer is a little involved. I would pause the video for a second and work it out yourself. The answer is length, because like under this transformation, like whatever the length between 2 points was, it's going to remain the same. It doesn't really change. The angle between 2 lines wouldn't change. I mean, the absolute angle of that line with respect to the horizontal changes, but the relative angle does not change. And as an artifact of this, the area would not change. Right? And if you remember like simple trigonometry, where the area of the triangle is given from length and angles, this is the same idea there. So how many number of variables or degrees of freedom we have? It's fairly simple. You add the 2 true from translation from before and 1 from rotation, and that gives you 3. Awesome. So how many point pairs would we need for this? So remember that each point gives you 2 equations. So we need a minimum of 3 equations, which means that we have to have 2 point pairs. Awesome. So now let's look at the rotation and translation again from a slightly different viewpoint. So we translate first and then we rotate. How would this look like? The order of the transformations flip, wherein you do the translation first and then you right multiply the rotation, right? Okay. So we basically are post multiplying our transformations because we are doing instantaneous transformations. I will have another video coming up, which is going to go into extreme detail of why this is the case. But if you just want to remember that you want to post multiply your transformations if you are doing doing the transformations based on the output of the previous case. If you are doing this with respect to a global axis like GPS or something like that, you are going to be pre-multiplying the coordinate transformations as you go along. Okay, let's look at scaling, wherein you have the second image as a scaled version of the other one. Remember that in this case, the scaling in the x direction and the y direction do not have to be the same, as you see here. So we are changing the aspect ratio. So I would want you to see that this is a fairly simple thing. You're just like multiplying the x values by sx and the y values by sy. And the number of independent variables here are 2, fairly simple. So shear is basically a transformation wherein the y and x are dependent. So the shear transformation looks like this. And again, it's like the off diagonal element in that transformation matrix. Great. So let's look at this transformation called a similarity transformation, wherein we have scaling, then we have rotation, and then we have translation. This is called Euclidean plus uniform scaling, or a similarity transformation. It's the same SE2 transformation from before plus uniform scaling, which is x and y scale are the same. And I want you to pause the video for a second and think about what the H transformation here would look like. So as you were thinking, H is the scale, then multiplied by rotation, then multiplied by translation. Okay, let's ask the question, what is actually invariant in this case? Remember that the length is not invariant like before because like we are scaling it, but the ratio between 2 lengths are independent. And of course the angle doesn't change, and the shape of a certain object doesn't change. If something was a square, it will remain a square. Of course, it won't be axis aligned anymore, right? How many number of degrees of freedom? You can add up the degrees of freedom for all of them. It's 4 because we have 1 for scale because it's uniform scaling. We have 1 for rotation, that's 2. And we have 2 more for translation, which is 4. And how many number of point pairs? Fairly simple, it's 2. Okay, Let's build up. Let's have this transformation called the affine transformation, which is going to somewhat look like a three-dimensional transformation. If you have ever used a computer-aided design or a CAD software in your life before, if you click on that orthographic projection button, this is exactly what is happening inside. So this is basically like if you're seeing a three-dimensional transformation from really far away, like as far as the sun or something, where the rays of light are parallel, it will look like the orthographic or the affine transformation. And the affine transformation is fairly simple. It looks like this. In this particular case, we don't have the nice functional form we had before. We just have these 6 numbers A11 to A23, and that's what it looks like. Where you have the rotation, shear, all these things mixed up into these values. So the question is, what is invariant? It's a little more involved here. I would want you to pause the video for a second and think about it. So the first one is collinearity, which means that if the multiple points lied on a straight line, it would lie on a straight line in the affine. I want you to observe one trend. As we are going along in transformations, there are lesser and lesser things which are invariant, and it's actually harder to actually imagine or envision these things. So one way to do this would be actually like write the equations down, write the equation relationship between 2 points, and actually work it out in math. Right? So the parallelism is invariant. If 2 lines were parallel before the transformation, they will still remain parallel after the transformation. And the ratios of length like before are going to be invariant. So how many degrees of freedom? This is fairly easy to see. You can read it off. It's 6 values. So number of point pairs is 3. Beautiful. So the most amazing transformation which actually mimics 3D in full glory is called the homography or the projective transformation. So in this particular case, there's a little star which says homography is basically a plane-to-plane transformation. This is essentially saying, okay, if I have a plane and I take the image of a plane from a completely different viewpoint, how does it look like? Okay. So as you would see, unlike the affine transformation where the lines were parallel, it looked like a parallelogram. In this case, it looks like a trapezium, right? So it's not really the same thing. So as you would expect, 2 more values get added to the affine transformation and it becomes 8 values in total. So pause the video, think about what actually gets invariant here. Lines will remain lines because we don't curve anything, and cross ratios will be preserved across transformations. And this is going to be one of the most beautiful tricks we are going to use in the future to actually estimate 3-dimensional information from this 2D transformation. Concurrency is going to be preserved, which means that if two lines intersect, they will intersect after the transformation as well. And collinearity is going to be preserved like before. How many variables does this have? Fairly easy to read, 8. Number of point pairs, fairly easy to see, 4. Great. So just to quickly recap, this is what it looks like. Pause the video, look at this, and it's a fairly simple thing. As you go from bottom to top, you add more and more degrees of freedom, and lesser things will get preserved. Beautiful. Just a quick understanding check. What is a transformation? How many degrees of freedom does affine transformation have? How many degrees of freedom does homography transformation have? See you next time. Take care. Bye-bye. Hopefully you will see transformations all around you from now on. Bye.